this video, we're going to discuss control strategies for chilled beam projects. Specifically, we're going to talk about chilled beam projects where the primary air is variable airflow, so that you can adjust that air based on the needs of the building. So here's the general layout that we're going to be that you would see. You're going to have an air handling unit, and we'll discuss how that's controlled here in a minute. It's supplying air into the building through the primary ductwork and then out through the branch ducting to the beams. Now there might be a VAV box for a group of beams, or the variable airflow control might be integrated into the beam. We'll look at both. And because it's a VAV system, a bunch of manual balancing dampers are not going to be particularly helpful. The system is going to operate over a very wide range of airflow rates and pressures, and so manual balancing dampers are not going to assist you. You're going to have dynamic airflow control from the VAV boxes or the beams themselves, and of course that you're going to have variable airflow on the fans. So let's talk a little bit about the primary air handling unit and the typical control sequences. So unlike a constant volume chilled beam system, you're now going to be able to vary the airflow. That means that these fans here are most likely going to have VFDs on them or some kind of speed controller. And a typical way to do that is to measure the pressure in the ductwork. It is a good idea to have that pressure sensor at the far end of the duct range. It's the most energy efficient way to do it, so at least 2/3 of the way down the ductwork. And that signal will be brought back to the air handling unit controller and would adjust the supply and the return fans. It's often common to see the return fan slaved to the supply fan, so as the supply fan slows down, the return fan matches that. You can have an offset. These are all typical things that are in a unit controller. And you'll notice that this air handling unit has got energy recovery. This is a very common thing to see done on a chilled beam system where you use 100% outside air into the building. But you want to use the exhaust air out of the building as either an energy source or an energy sink to help reduce the load on the chilled water coils and the hot water coils here. And they're normally chilled water and hot water because, being a chilled beam project, you already have hot water and chilled water available in the building, so it's pretty common to see these things as coils. So that was the airflow is going to be varying. Let's talk a little bit about the temperature. So here for a chilled beam system, it's going to be discharge air temperature control. So there'll be a temperature sensor in the supply duct that the controller will use against a set point somewhere between 55 and 75 degrees. There isn't a right or wrong here. It's about how the building is being designed and how the building's being used. But whatever that set point is, the controller will try to optimize the energy recovery first, and when that's not enough, it'll supplement it with chilled water and hot water. And you can also, for a chilled beam system in a very hot and humid climate or with a lot of internal humidity gain, you might also be looking at having some form of reheat. So being able to cool the air down and then reheat it. And if that's true, you may have some extra temperature sensors or a humidity sensor in the return duct or the supply duct that's being used to control the algorithm to dehumidify the air, wring the moisture out, but then bring the air back up closer to the dew point of the space, which is usually around 55 degrees. Now, another common thing that you'll see done on the air handling units is that they'll supplement the air handling unit with a recirculating section. So you can see that we're mixing some return air into the supply air side with outside air. Works out that if in a chilled beam system, that the primary air is usually greater than what you need for minimum ventilation for the outdoor rating of the building. So if I picked an office building as a specific type, typically the ventilation rate is somewhere around 0.11 to 12 CFM a square foot, and yet the primary airflow rate would be closer to 0.3 CFM per square foot in the chilled beam system. So we could bring in 1/3 of the air that we need from the back and recirculate 2/3 of the air around, still do the energy recovery on the air that's being exhausted to help take the load off the outside air, and then supply that to the space. So that's a very common arrangement to see done as well. Now, one of the nice things if you add a mixing box here is what do you do at night when the building is shut down? In the summer, the building could warm up. In the winter, the building could cool down to a point where you need to start adding some heat into some zone somewhere in the building that's getting outside of even the unoccupied set points. And you got to remember that without air flowing through a chilled beam, you cannot add heat through the chilled beam. There will be no air movement, so opening the hot water valve or the chilled water valve at a beam will not add any energy to the space or extract any energy from the space. So you need to start up your primary air handling unit and get some air out there. But you certainly don't want to have to start bringing 100% outside air into the space. So if you have a recirculating section, you can leave your outdoor air dampers closed. You can leave the exhaust fan off. Just start the supply fan. In most cases, you would not do any supplemental heating or cooling. This is building air. You just pass this thing through. It'll pressurize the duct based on the pressure controller. And at that point, whatever beams are servicing the zone that is too hot or too cold will have the primary air they need to be able to start adding some heat and cooling. And once that zone is satisfied to the setback conditions, the whole system can shut back down again. Well, let's start to zero in on what happens in the specific control zones. So what we have here is the primary air. In this example, you can see a VAV box has been added to the branch duct that services a zone. And let's just talk about this zone. We could break it down and start talking that each chill beam is a zone unto itself. It's actually a very expensive way to do it. And so we would recommend that you look at breaking the building into control zones just the same as you would do with a VAV system. So if there was a classroom, it would be a control zone. If it was a hotel room or a patient room, it would be a zone. Conference room, office, these would all be zones. And you'd use the same logic that you would use for any kind of control zone breakdown. And that means that the building automation system is going to have a unit controller, this thing right here, for the control zone. And in most cases, you're going to have more than one chill beam in that space. You might have anywhere from 3 or 4 or 6 chill beams, depending on how big the control zone is. And this controller is going to treat all the beams the same. And that will provide even heating and cooling throughout that space. So the controller is here. It's going to monitor the temperature in that space. We're going to talk about that. It could be measuring the indoor air quality, the CO2, and we're going to keep an eye on the dehumidification of the dew point issue. So we're going to monitor all 3 of those things in this control zone. The controller is hooked to a chilled water valve that would service all 4 beams in this example. So when that valve opens, chilled water would make it to all 4 beams. The other one here, the gray one, is the hot water valve. And it too would service all 4 beams. And so the controller can modulate the airflow, modulate chilled water, modulate hot water, and is monitoring the temperature of the CO2 and the dew point of the space to make all the decisions. Now, this is a really good system. It's very popular. It lets you use standard chilled beams in the system design. Now what happens though is a chilled beam has a nozzle in it, and its size has been specifically picked for its airflow rate and its design conditions, and so it's been optimized to give you the right induction rate that you want for that beam for the application. The moment that you change the airflow going to that beam, it very quickly gets out of tolerance for the nozzle. And typically what happens here is if you reduce the airflow more than about 30% down from whatever the proper setting is, the induction process really starts to drop off, and you may not be able to actually induce any air to go through the coil. So a VAV box can typically modulate somewhere between 100 and 70% of airflow in this approach before the chilled beams themselves would stop being able to induce air. But this is still a significant amount of energy savings, and so this is a very nice approach. In the last slide, we were looking at a VAV box installed in a branch duct that served a group of chilled beams. But you can also actually integrate the VAV function right into the beam. So in this video, you can see how there is the plate is sliding back and forth, and it's doing 2 things. It is limiting the primary airflow into the beam, but it's also adjusting the amount of nozzles that are available. So it's synchronizing a change in the nozzle setting with the change in the primary airflow rate. And that allows the beam to have a much greater turn down range. And so what you get is an actuator down here that would drive that. So there'll be an actuator on every chilled beam, and they'd be typically 0 to 10 volt signals. They would all be wired back to the zone controller. So instead of controlling one actuator on a general VAV box, you're going to control an actuator per beam. But what you get is greater rangeability because the beam can adjust the nozzles at the same time as adjusting the airflow rate. And there's different technologies out there on how those nozzles adjust with the integrated VAV airflow. So let's have a look at an integrated solution in here. You can see that the VAV damper is actually built into the beam, and all these actuators would be wired back to the unit controller for the space. We're going to be measuring the temperature, the indoor environmental quality, and we're going to be measuring the dew point of the space. There's a pressure sensor that's being used by the air handling system. The more of these dampers that open up, the pressure will start to drop. That'll cause the air handling unit fans to speed up and rebuild the pressure so that we can vary the primary airflow rate based on what's actually needed in all the different zones. And because we're using some form of integrated solution in here, we have a much greater turn down. We can typically turn the air down about 3 to 1, so from 100 to 33 per 30% airflow. Down through here. And often how much, one of the things you need to know is how much air is actually going through this beam. We want independent control. We don't want to say that, hey, if we need 50% airflow, open the damper 50%. That's dependent control. And the problem is the actual airflow that goes through the beam would be completely dependent on what the pressure was in this ductwork right here at any given point in time. And throughout the day, that's going to change significantly. So what you really want to do is to say, I need to have 50% airflow right now. Let's measure the airflow and compare it to 50%, and then adjust the dampers so that only 50% air comes through the beams. That's independent control, but it does mean you need an airflow rating. A couple of ways you could do that. Sometimes they measure the pressure drop across the nozzles inside the beam, so there would be a pressure transducer. You would not need a pressure transducer on all 4 beams. One would be enough. So in a zone like this, you might have what might be referred to as a master beam with some extra sensors. That pressure transducer would be wired to the unit controller, and it would use that signal to say to work out what the airflow rate was, and then adjust the signal to all 4 beams. So you'd have a master and then 3 common beams here that didn't need the pressure sensor. You might have an airflow sensor in here as well. Whatever it is, you're going to get a signal out of it that the unit controller can use to calculate the airflow rate that's going into the space. And the chill beam manufacturer should be able to give you the K factor for whatever technology they promote that would allow you to calculate backwards once you know the pressure and the K factor for the unit controller to be able to calculate the airflow. Well, let's start to look at what happens if we have a cooling load. And unlike a constant volume system, as a designer, you now have an interesting choice. If we're going from a situation where there's no load to load, we have to decide, we have 2 ways we could cool that space. We could increase the primary airflow. It's 55 degrees. It will absolutely air condition the space. Or we could open the chilled water valve and let water flow through these beams, and that would cool the space. And so the question becomes, which one do you want to do? Do you want to do water before air, which is shown here, or do you want to do air before water? So we'll just walk through the control sequences and how the system behaves, and then we can have a quick conversation about the logic of picking one over the other. There's not a right or a wrong answer. It's very much project specific. So in this example, as we go from no load to load, the priority is going to be given, try to do the cooling first with water, and if that's not enough, to do it with air. That's what we mean by water before air. So let's start with the space being neutral. So we're inside our deadband. The system is balanced. The temperature reading is matching the temperature set point within the deadband, and so there's no call for action by the system. So it stays balanced. Now we start to see an increase in cooling load. And so the first thing the controller will do is it will leave the primary air at the minimum airflow. And typically minimum airflow is what's required by standard 62. And so that you know that you're always getting the right amount of ventilation air in here. And we're going to leave that there so you can see we're not changing the ventilation air yet. But we'll start to open the chilled water valve here and modulate flow to all 4 beams and see if we can meet the cooling load by just using water. Well, it happens now is that the load continues to increase, and even though with the chilled water valve fully open and we're at design flow, we still can't meet the cooling. So now what happens is the controller goes to effectively stage 2, and it starts to open up the air valves, and it changes the airflow set point, increasing from minimum, which like I said was usually 62, and just linearly up to 100% of design airflow. And as you add the air in here, you improve, you get the cooling effect of the air, but you also get the induction rate that air causes, so it pulls more room air through the beams. And so this actually gives you quite a kick here at the end in terms of the amount of cooling that you can get. Okay, well, let's go back and reset what we did before, but this time let's look at cooling loads, but we're going to prioritize the air before the water, and let's understand what happens to that sequence. So again, we're going to go back and start at neutral, which means we're at minimum airflow rate here. This would be less than design airflow rate. It would be typically what's required for standard 62 to meet indoor air quality, and but the space is satisfied, and so there's no activity or adjustment that needs to happen. And then we see the loads start to increase. And in this case, the controller will start to increase the airflow rate to the beams before it increases the chilled water. And so it'll let more primary air into this space. It'll reset the airflow rate from minimum airflow to design airflow, typically in a linear line based on the load and the distance from set point. And so it'll adjust that up, and more primary air will enter the space. And most systems are designed with 55-degree air, so this is going to provide cooling to the space and very good indoor air quality as you're increasing the amount of primary air to the space. And then, of course, the load continues to rise, and the air itself is no longer enough to meet the load, and so we have to start adding chilled water to the space. And so as you move into this range, the controller will have gone to 100% airflow, and then it'll start to modulate the chilled water valve open to meet the load. And remember, that valve is going to service all 4 beams, so when it opens, all the beams get water. So why would an engineer pick water before air or air before water? There isn't a right or a wrong answer, but we could give you some quick advice. Generally speaking, the efficiency or the energy usage of the building will be lowest if you try to cool the building with water versus air. It just costs a lot more to move air around the building than it does water. And so if you can get the heat out of the space using chilled water versus cooled air, that'll be your lowest energy cost. And so on average, we would say that if the priority here is to have the best EUI, the best energy use intensity, you should try water before air. But there are a couple of exceptions. Well, first is, depending on your climate, it may actually be advantageous to you to go straight to air. And take, for example, the Pacific Northwest in Seattle. They have so many economizer operating hours that, yes, they'll spend more energy on their fans bringing air to the spaces, but they didn't have to condition that air because they're in economizer mode. And so while their fan work goes up, their chiller plant or their heater plant work goes down. And when you run the energy models for the same building and move it from, say, Chicago to Seattle, you'll actually find that it'll be cheaper if you go air before water, just because of the economizer hours. Another example where we might recommend that you go air before water would be in a place that has a very large internal latent load. An example would be a large lecture hall at a university where you're going to go from no load to full load in 5 minutes, and you have a lot of people move in, your humidity will go up, and it's generally a good idea to get in front of your indoor environmental load that is going to happen very quickly, and the humidity from all those people. And so we would recommend that from the occupant experience, they're going to enjoy that space the most if you go air first and then water. But there is no right or wrong answer to it, and generally you could switch that if in the commissioning process of that to service the customer's needs. So we talked about cooling. What happens when you have an integrated VAV solution and you start talking about heating? So in this case, we have 4 pipe chill beams, meaning that there's a separate hot water coil in the beams. By the way, you could have a hot water coil in the ductwork if you wanted to and just try to crank the heat up into the air, but it'll get energy into the space. and that hot water valve is wired to our controller. And so we have control with the air and we have control of the water. So let's walk through our sequence here. We're going to start with the space being balanced, so it's inside the dead band, so the set point and the temperature, the actual temperature, are matched, so the unit will stay in its neutral operating point. It's going to be down at minimum airflow, again just meeting standard 62 requirements. So what happens when the temperature starts to drop in the space and we move here? Well, we're at minimum airflow rate. The first thing you need to do is to turn on the hot water. And so it's always going to be water first. You have to remember that this air is typically 55 degrees. So even this small amount of air coming in space is actually adding to the air conditioning load to the space. It's cooling the room down. And so the first thing the hot water has to do is to offset the heat, to just warm this air up from 55 to 75 just to make it neutral, and then after that it will start to add heat to the space. So the first thing that's going to come on is the water, and you can stay at minimum airflow and ramp that water valve from 0 to 100% and see if you can meet the load. And of course, if the load can't be met with that, you're actually going to have to run more air through the beams. That might sound counterintuitive when you're saying, why would I put more 55-degree air into the space? But you have to remember that a typical beam in an office application has an induction ratio of 3 to 1, meaning that for every CFM you put in, we're going to pull 3 CFM from the room through the heating coil and put it back in the space. So yes, you are going to heat this air from 55 to 75, but you're also going to heat 3 more CFM from the space from 75 to typically around 90 degrees off the coil, and then that will add energy to the space. And so we only increase the airflow rate when we have to, so a very high demand, heating demand. Well, let's talk about dew point control. So it's always an important discussion when we're doing a chill beam project to consider how we are going to manage dew points in the space. And that's important because chill beams are sensible only devices. There are no drain pans, there is no condensate piping. If this space dew point gets above the dew point of the coil, and most people would use the chilled water inlet temperature of 57 degrees, if the space is allowed to get above that, slowly condensation will start to form on the coil. It could drip. It would definitely not be a satisfactory situation for the building occupants or the building owner. And so it's important that we have strategies to deal with these unusual events. This shouldn't happen. What dries the space out, if the chill beams can only do the sensible heating and the sensible cooling, what dries the space is the primary air. And its cyclometric conditions were picked to meet the demand humidity load of that building. So that air flow rate and its dew point of the primary air is dry enough to meet the space conditions. But that doesn't mean that something unusual couldn't happen. An example would be that somebody props doors open in the middle of summer. They're moving furniture in or something like that and allow a whole bunch of hot and humid air to enter the space. Another one is that somebody uses the space in a way that was not expected. Put a whole bunch of people in a room that was not expected to have a lot of people in it. And so we can have situations be created where we run a risk that we're getting very close to dew point. In this picture, we're showing you a couple of different typical control devices that you would see used with chill beams. This one is a dew point sensor, and it's actually mounted on the coil and the beam itself. So as the room air is drawn in through this coil to be heated and cooled, it's actually flowing right over the sensor, and so we get a very good reading of the condition of that space. You would not need to put one of these on every chill beam in a control zone. You only need one. So back to that concept of having a master chill beam, you could put a dew point sensor right on the beam and leave the other 3 as common chill beams, just have it here. Or the building automation company may have a dew point sensor that is part of their wall sensor assembly. Either one would work to get a reading. So this one is going to measure dew point. So it's going to recognize that the humidity is climbing in the space. You're getting close to dew point. You need to start thinking about corrective measures. So it is the preferred way to do it because it is preventative. It's proactive in its response. Down here is another type of sensor. It's a condensate sensor, and it's typically strapped onto the chilled water inlet pipe, which is going to be the coldest thing in the space, right? Normally the chilled water is 57 degrees. And so this sensor would be mounted on it, and if the humidity got high enough, if the dew point got high enough in the space and condensate started to form on this pipe, this sensor would pick up the liquid water. And when that happens, it would let the building automation system know that you actually had a problem. So this is a little bit after the fact, but it would tell you in time to start taking some pretty aggressive corrective measures to stop from damaging the building. Now, there are multiple sequences of things that you can do about turning off chilled water valves and other things. They were covered in some detail in the constant flow control sequences, and certainly offer or recommend that you go and listen to that section to see about some of those actions. You can do them with a variable airflow system as well, but there's some things you can do with the variable airflow system that are very attractive, and we're going to talk about those right now. So let's go back to our system. We have integral chill beams in here. We can vary the airflow rate. We can vary the hot water and the chilled water. This is all being controlled from the zone controller. Even though there's multiple beams in here, we treat all the beams the same. But we have some form of dew point or humidity sensor, like you saw in the last picture. And if this is if the space is below dew point at any operating condition, then what you do is you stay quite neutral here. So you're in the neutral band. You're not going to do anything. It's your normal control sequences. You might have a little bit of chilled water on. You might have increased the ventilation air. Whatever the sequence is, there's no overriding action because you're below your dew point set point. Well, let's consider what happens if the dew point starts to climb, and we're now getting above where we want it to be. So you're in here. Now, you had a cooling load before. You might have been able to satisfy that cooling load with some combination of water and air. But all of a sudden now what's going to happen is you are going to override your temperature control and say, hey, I know I had the space satisfied with a percentage of primary air and a percentage of chilled water, but I now have a situation where the dew point is higher than I want it to be in the space. Well, how do you dry a space out? You increase the primary airflow rate. So you would override whatever the calculation was to meet the temperature and say, I actually would like to meet the cooling load with more air and less water. So I don't want to do more cooling in the space. I don't want to overcool the space. I want to meet the load, but I want to do it with less water and more air, and that air will start to dry the space out. It's a very straightforward control sequence for the controls contractor to do. And what he would do is just start to increase the airflow rate into the space and decrease the chilled water to meet the maintain the set point, the temperature, but also to provide the air, which is the fluid that's going to dry the space out. So we've talked about this ability to increase the airflow rate to dry the space out when you have a high humidity load. And you have to remember that primary air was set for a design day, which happens very rarely. So it's a big advantage from an energy point of view to not supply primary air if you don't have to. That's the great thing about being able to measure the dew point and say, I'm only going to go to design airflow rate if I need it. And if I don't need it, if I don't have the humidity loads, then I'm going to cut back and get the energy savings. In a constant volume system, you're always at design airflow rate. And so you shouldn't have an issue, but it also means you're operating at a very high airflow rate for most of the time, even though you don't need it. Let's talk for a second about indoor air quality. So common to put a CO2 sensor on it. If this was a multiple person space, a CO2 sensor is a great way to go. You could also use a VOC sensor. They're popular in Europe. That'll do the same thing. It's really going to measure some parameter in the space to let you know whether or not the indoor air quality is starting to degrade. And we're going to have the same kind of situation we had before, right? So we've got a situation in here where we're within tolerance. If it's CO2, most people would say you got to stay below 700 parts per million above background. Well, that would be kind of your high limit. So if we're less than that, we wouldn't override the normal controls. The system will focus on meeting the temperature, and to meet that temperature, it'll have some combination of primary air and chilled water. It'll satisfy the cooling. Everything would be normal, but what we're starting to see is that the CO2 level is climbing in the space. And so when that starts to happen, when we see the CO2 climb up, the same thing that happened in the dew point control is going to happen in the CO2, which is we're going to say we want the same overall cooling effect. We had satisfied the space before, but we're going to do it with less water and more air. So, and that air will introduce the ventilation air that we need to improve the indoor air quality. This is demand control ventilation at the beam level. And so it's a very good way to help minimize your energy consumption in the building. Let's not bring that air into the space unless we have to, but now you know when a zone needs help and when it needs better ventilation. And you can do this control zone by control zone. So you were not going to ventilate the whole building just because a couple of zones have a high occupancy level. So that's a quick discussion about control algorithms and sequences for a VAV chill beam system. Thank you very much.